The local volume is the set of galaxies covered in the Local Volume Legacy Survey, or LVL for short, conducted by the Spitzer team. It is a complete sample of 258 galaxies within 36 million light-years. This montage of images shows the ensemble of galaxies as observed by Spitzer. The galaxies are randomly arranged, but their relative sizes are as they appear on the sky. Here we have the galaxies laid out by distance from us. We'll take a look at a number of them. The dwarf galaxy NGC 4214 is ablaze with young stars and gas clouds. The galaxy's close proximity, combined with the wide variety of evolutionary stages among the stars, make it an ideal laboratory to research the triggers of star formation and evolution. Intricate patterns of glowing hydrogen form during the star-birthing process, cavities blown clear of gas by stellar winds, and bright stellar clusters can be seen in the optical and near-infrared image. Resembling looming rain clouds on a stormy day, dark lanes of dust crisscross the giant elliptical galaxy Centaurus A. Hubble's panoramic vision, stretching from ultraviolet through near-infrared wavelengths, reveals the vibrant glow of young blue star clusters, and a glimpse into regions normally obscured by the dust. The warped shape of Centaurus A's disk of gas and dust is evidence for a past collision and merger with another galaxy. The resulting shock waves cause hydrogen gas clouds to compress, triggering a firestorm of new star formation. At a distance of over 11 million light-years, Centaurus A contains the closest active galactic nucleus to Earth. The center is home for a supermassive black hole that ejects jets of high-speed gas into space, but neither the supermassive black hole nor the jets are visible in this image. But they are in this one. This color composite image of Centaurus A reveals the lobes and jets emanating from the galaxy's central black hole. This image showcases the brilliant core of one of the most active galaxies in our local neighborhood. The entire core is 5,000 light-years wide. NGC 1569 sparkles with the light from millions of newly formed young stars. It is pumping out stars at a rate that is 100 times faster than the rate observed in our Milky Way. This frenzied pace has been almost continuous for the past 100 million years. This beautiful galaxy is tilted on an oblique angle, giving us a bird's eye view of this grand design spiral galaxy. It is similar to our Milky Way, but this favorable view provides a better picture of the typical architecture of spiral galaxies. The spiral arms, which wind all the way down into the nucleus, are made up of young, bluish, hot stars formed in the past few million years. A number of sinuous dust lanes also wind all the way into the nucleus of M81. A black hole of 70 million solar masses resides at the center. This is about 15 times the mass of the Milky Way's black hole. Hubble research shows that the size of the central black hole in a galaxy is proportional to the mass of the galaxy's bulge. This loose collection of stars is actually a dwarf irregular galaxy called Holmberg IX. It resides just off the outer edge of M81, Holmberg IX is of the so-called Magellanic type of galaxy, as its size and irregularity in structure are similar to the Small Magellanic Cloud. A close encounter with M81 may have triggered the new star formation that has occurred. By understanding how Holmberg IX was formed, scientists hope to understand their role as building blocks for larger galaxies. Here we are zooming into M82. The galaxy is remarkable for its bright blue disk, webs of shredded clouds, and fiery-looking plumes of glowing hydrogen blasting out of its central regions. Throughout the galaxy's center, young stars are being born 10 times faster than they are inside our entire Milky Way galaxy. A huge concentration of young stars has carved into the gas and dust at the galaxy's center. The fierce galactic superwind generated from these stars compresses enough gas to make millions of more stars. Young stars are crammed into tiny but massive star clusters. These in turn congregate by the dozens to make the bright patches or starburst clumps in the central part of M82. Most of the pale, white objects sprinkled around the body of M82 that look like fuzzy stars are actually individual star clusters, about 20 light-years across and containing up to 1 million stars each. This galaxy is called Circinus. Much of the gas in its disk is concentrated in 2 specific rings. A larger one, 1,300 light-years wide, and a previously unseen ring, 286 light-years wide. Both rings are home to large amounts of gas and dust, as well as areas of major starburst activity. At the center of the starburst rings is the supermassive black hole that is accelerating surrounding gas and dust. The black hole and its accretion disk are expelling gas out of the galaxy's disk into its halo. The detailed structure of this gas is seen as magenta-colored streamers extending towards the top of the image. Located near the plane of our own Milky Way galaxy, the Circinus galaxy is partially hidden by intervening dust along our line of sight. As a result, the galaxy went unnoticed until 1999. Nicknamed the Southern Pinwheel, M83 is undergoing more rapid star formation than our own Milky Way, especially in its nucleus. This Hubble close-up has captured hundreds of young star clusters, ancient swarms of globular star clusters, and hundreds of thousands of individual stars, mostly blue supergiants and red supergiants. The remains of about 60 supernova blasts can be seen in the image. Hubble has taken a beautiful picture of NGC 6503. It spans some 30,000 light-years. In this image, bright red patches of gas can be seen scattered through its swirling spiral arms, mixed with bright blue regions that contain newly forming stars, with dark brown dust lanes snaking across the galaxy's bright arms and center. This barred galaxy is about half the size of the Milky Way. Astronomers estimate that 2/3 of all spiral galaxies have a bar structure at its center, including the Milky Way. The swirling spiral arms are the birthplace of new stars. Their high temperatures make them shine blue. Clouds of dust and gas distributed through the spiral arms, glowing red in the image, are reservoirs of material for even more stars. The bright stars on the left are Milky Way stars in the line of sight to NGC 3344. The Large Binocular Telescope, LBT for short, in Arizona, was scanning the Fireworks Galaxy, 22 million light-years away, looking for supernova candidates. They examined the star named N6946-BH1, a star 25 times more massive than our Sun. Stars this size usually end in a supernova explosion, leaving behind a neutron star or a black hole. Here's a graph of the star's luminosity in visible and infrared light over time. In 2007, Hubble took this picture of the star. In 2009, the star shot up in brightness to become over 1 million times more luminous than our Sun for several months. The expectation was it was about to supernova. But it didn't. It just seemed to vanish, as seen in this image from 2015. After the LBT turned up the star, astronomers aimed the Hubble for visible light and Spitzer for infrared light to see if the star was still there. All tests came up negative. The star was no longer there. The researchers eventually concluded that the star must have become a black hole without a supernova. It has been estimated that up to 30% of all massive stars form black holes this way, with the remaining 70% taking the supernova path. Here's the magnificent spiral galaxy M106. It is a class of galaxy called a Seyfert galaxy. Seyfert galaxies account for about 10% of all galaxies and are some of the most intensely studied objects in astronomy, as they are thought to be powered by the same phenomena that occur in quasars, although they are closer and less luminous than quasars. These galaxies have supermassive black holes at their centers, which are surrounded by accretion disks of infalling material. The accretion disks are believed to be the source of the observed ultraviolet radiation. Tightly wound, almost concentric arms of dark dust encircle the bright nucleus of galaxy NGC 2787. This lens-shaped galaxy shows little or no evidence of any grand spiral arms. Also visible in the image are about a dozen globular clusters hovering around the galaxy. What appears to be stars are in fact gravitationally bound families of hundreds of thousands of ancient stars orbiting the center of NGC 2787. The irregular galaxy NGC 4485 shows the signs of having been involved in a collision with another galaxy. The right side of the galaxy is ablaze with star formation, shown in the large number of young blue and pinkish star birth nebulas. The left side, however, looks intact. It contains hints of the galaxy's previous spiral structure, which, at one time, was undergoing normal galactic evolution. Here's the other colliding galaxy, NGC 4490. The two galaxies sideswiped each other millions of years ago and are now 24,000 light-years apart. The gravitational tug-of-war between them created rippling patches of high-density gas and dust within both galaxies. Here we are zooming into the Pinwheel Galaxy M101. This is the largest and most detailed photo of a spiral galaxy that has ever been released from Hubble. The galaxy's portrait is actually composed of 51 individual Hubble exposures, in addition to elements from images from ground-based photos. The giant spiral disk of stars, dust, and gas is 170,000 light-years across, or nearly twice the diameter of our galaxy. M101 is estimated to contain at least 1 trillion stars. Approximately 100 billion of these stars could be like our Sun in terms of temperature and lifetime. This is the Sombrero Galaxy. The galaxy's hallmark is a bright white bulbous core encircled by the thick dust lanes comprising the spiral structure of the galaxy. It is 50,000 light-years across. M104's rich halo system of nearly 2,000 globular clusters is 10 times as many as orbit our Milky Way. Embedded in the bright core of M104 is a smaller disk, which is tilted relative to the large disk. X-ray emissions suggest that there is material falling into the compact core, where a 1 billion solar mass black hole resides. Here's what Sombrero looks like in infrared from Spitzer. NGC 1512 is a barred spiral galaxy spanning 70,000 light-years. The galaxy's core is unique for its stunning 2,400 light-year wide circle of infant star clusters called a circumnuclear starburst ring. In this view of the center of the magnificent barred spiral galaxy, Hubble's broad spectral vision reveals the galaxy at all wavelengths from ultraviolet to infrared. The colors, which indicate differences in light intensity, map where newly born star clusters exist in both dusty and clean regions of the galaxy. Here's a deep dive into the Whirlpool Galaxy M51. These images of the Whirlpool Galaxy highlight the attributes of a typical spiral galaxy, including graceful, curving arms, pink star-forming regions, and brilliant blue strands of star clusters. In the early days, when knowledge of spiral arms around galaxies was relatively new, astronomers thought that they were made of material and orbited the center of the galaxy just like stars, dust, and gas. Our Whirlpool Galaxy is a good model for this. But as star motion within galaxies became better understood, we found that the stars near the center have a much shorter orbital period than the stars further away from the center. For example, in our Milky Way, stars near the central bulge can complete a revolution around the central bulge in about 90 million years. Out here, 26,000 light-years away from the center, it takes 230 million years. And in the outskirts, it can take over 400 million years. It followed that if the spiral arms were rotating with the stars, its structure would be lost in just a few rotations. You can see in this simulation that even after just one revolution, the arms would change significantly, with the inner galaxy areas being stretched more than the outer galaxy areas. In astronomical terms, we would see spiral arm structure disappear in short order. But from all we see from spiral galaxies of all ages, the spiral arm structure does persist over billions of years. This disconnect is called the winding problem. Clearly, the spiral arms do not rotate with the stars, dust, and gas. The density wave theory was proposed by C.C. Lin and Frank Hsu in the mid-1960s to explain the spiral arm structure of spiral galaxies. The theory holds that spiral arms are not material in nature, but instead are made up of areas of greater density. The stars, gas and dust in a galaxy, move around the center in elliptical orbits. If we simply assume that an orbit's major axis shifts slightly as the distance from the center goes up, we can reconstruct the spiral arms as we see them in real galaxies. Lin and Xu, examining magnetic fields, gas distributions, and star velocities, showed that this kind of grand design spiral pattern could persist indefinitely if the pattern also rotated, but with the outer portion of the arms rotating faster than the inner portions. By their calculations, a typical pattern velocity is around 0.004 kilometers per second per light year. That is, the velocity of the pattern goes up 4/1000ths of a kilometer per second for each light year the pattern location is from the center. For our star, 26,000 light years from the center of the Milky Way, we have a pattern velocity for the Orion spur at around 100 kilometers per second, or 65 miles per second. Our star's velocity around the center is more than twice that much. I expect we'll be leaving the Orion spur in a few million years. Here's a look at a gas cloud orbiting around a galaxy in the spiral pattern's frame of reference. As it approaches the spiral arm, it gets compressed as the orbiting molecules within the cloud move closer and closer together. This compression effect is thought to trigger cloud collapse. This in turn creates new stars. The most massive blue stars don't burn long enough to make it through the spiral arm before they run out of hydrogen fuel in supernova. That explains why we only see these giant blue stars in the trailing edge of spiral arms. Normal yellow and lower mass red stars exist for much longer and exit the spiral arm and orbit the galaxy for billions of years. It's important to note that just how these spiral arm structures form in the first place is still not understood. Here we are zooming into Messier 74, a stunning example of a grand design spiral galaxy that is viewed by Earth observers nearly face-on. Its perfectly symmetrical spiral arms emanate from the central nucleus and are dotted with clusters of young blue stars and glowing pink H2 regions of ionized hydrogen. Tracing along the spiral arms are winding dust lanes that also begin very near the galaxy's nucleus and follow along the length of the spiral arms. Here's a deep look into M66, the owner of unusually asymmetric spiral arms which seem to climb above the galaxy's main disk and a displaced nucleus. Astronomers believe that M66's once orderly shape has most likely been distorted by the gravitational pull of its two neighbors. M66 boasts a remarkable record of supernova explosions. The spiral galaxy has hosted 3 supernovas since 1989, the latest one occurring in 2009. M96's core is also displaced from the galactic center. Its gas and dust are distributed asymmetrically, and its spiral arms are ill-defined. But this portrait, taken with ESO's Very Large Telescope, shows that imperfections can be beautiful. The galaxy's core is compact but glowing, and the dark dust lanes around it move in a delicate swirl towards the nucleus. The spiral arm's patchy rings of young blue stars are like a necklace of blue pearls. Its graceful imperfections likely result from the gravitational pull from nearby galaxies. M96 spans 100,000 light-years in diameter, about the size of our Milky Way. In 1926, There were enough galaxies known for Edwin Hubble to create a morphological classification scheme. This is his diagram. His students called it the Hubble tuning fork. Hubble's scheme divides galaxies into three broad classes based on their visual appearance. Elliptical galaxies have smooth, featureless light distributions and appear as ellipses in images, like Centaurus A. They are denoted by the letter E followed by the integer n, representing the degree of ellipticity. Spiral galaxies consist of a flattened disk with stars forming a spiral structure and a central concentration of stars known as the bulge, like the Whirlpool Galaxy. They are given the symbol S or SB if it has a bar core followed by a letter A through C. As we move from A to C, the spiral arm structure becomes more open, the amount of dust in young stars decreases, and the central bulge of the galaxy decreases in size relative to the disk size. Lenticular galaxies also consist of a bright central bulge surrounded by an extended disk-like structure, but unlike spiral galaxies, the disks of lenticular galaxies have no visible spiral structure and are not actively forming stars in any significant quantity. NGC 2787 is an example of these. They are designated S0. These broad classes can be extended to enable finer distinctions of appearance and to encompass other types of galaxies, such as irregular galaxies, which have no obvious regular structure, either disk-like or ellipsoidal. The Large Magellanic Cloud is an example of this. Since Hubble, others have added characteristics such as bars, rings, and spiral arm characteristics. We lost parallax when we went beyond the nearby stars, but so far, the rest of our distance ladder has taken us through the local group and the local volume. But at the outer reaches, our Lyra variables leave our list. They are just not bright enough to be seen well beyond 20 million light-years. But Cepheids, H2 regions, globular clusters, Type 1a supernova are all going strong. They will take us well into the Virgo supercluster, our next segment.